Okay, so this is the second video for section 14.4, which is about tangent planes and linear approximation. And in the previous video, I covered tangent planes. And what you see here is sort of like a recap of the previous video. Namely, suppose you are given z is equal to f of xy, and you get some surface like this. And if you look at one point on the surface, ABC, where C is the z value at x is A, y is B, and then the equation of the tangent plane is given in this way. Namely, the equation of the plane, which is tangent to the surface at this point ABC, is given this way, z is equal to blah, 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 like this. And this is just a generalization of what you do in calculus 1. In calculus 1, you have like a y is equal to f of x. And if you look at A, and the equation of tangent line is given by the derivative, and then x minus A, and plus B. And then the equation of the tangent plane is pretty much the generalization of what you do in calculus 1. Then now, in this video, using this, I'm going to cover the concept of linear approximation, and after that, I'll introduce another concept called a differential. And this video, by the way, is going to be a little bit theoretical. Anyhow, then now, let's look at this equation of tangent plane. What does this mean? This means that z value of each point on the tangent plane is given this way. But if your xy values are close to this point ABC on the surface, that means your plane is pretty much a good approximation of the z value for the surface. Namely, if xy is close to AB, namely, if you are around this point AB, 0 to be precise, then the z value of the function itself, namely f of xy, is very close to the z value of the tangent plane. The tangent plane. Well, to be more precise, f of xy for this surface is approximated by here, the right hand side here, f sub x, AB, x minus a, plus f sub y, AB, y minus b, plus c, but c is the z value of the function. So a, b. Oops. All right. And then this is called the linear approximation of the z value of the function f of xy at AB. And then this right-hand side, the right-hand side is called a linearization of f of x, which we denote by L of x. So this is a linear function of x and y, L of y, and then this is called linearization. F of xy. And then, like I said, this identity here is called linear approximation. Of the z value of the function f of xy at AB. All right. And then indeed, you could actually verify that this linearization, the right-hand side of this equation, approximates the value of the function. For example, let's say let f of xy be x e to the power of xy, for example. Then find the linearization of xy at xy is equal to 2, 0. So let's do this problem. So what you have to do is just to compute the partial derivatives and plug into the formula. F sub x. So let's compute the partial derivative. You differentiate with x. So here you have to use the product rule. X e to the power of xy times y. Okay, to compute this, you have to use the chain rule. And then now, we are trying to find the linearization at 2, 0. So you have to plug in 2, 0 to here. And then you will see that this is equal to 1. And similarly, the partial with y is, so you just differentiate this with y. Excuse me. Then you get x squared e to the power of xy. And then this gives you f sub y of 2, 0. So you plug in 2, 0, you get 4. Okay. So therefore, and also, okay, to compute the linearization, you have to compute the value at 2, 0. Value of the function, z value of the function at 2, 0. So you just plug in 2, 0 here, and you get 2. All right. Then therefore, the linearization xy is given by this formula here. So it's 1 times x minus a, but a is 2, plus 4 times y minus 0, and then z value is 2. Okay, and then if you simplify this, you will see that this is equal to x plus 4y. So this is the linearization of this function. So this means, so essentially that's the answer, but this means, what does this mean? This means the value of the function, namely the value of x e to the power of xy, is approximated by this, x plus 4y, as long as you are close to 2, 0. X is close to 2 and y is close to 0. If your xy is close to 2, 0, the value of x times e to the power of xy is approximated by this simple expression. And indeed, you could actually you could just compute it by using calculator that f of, so something close to 2, 0, let's say 2.1 and negative 0.1. That's close to 2, 0. And then if you plug this into this side, you get 2.1 times e to the power of 2.1 times negative 0.1. And if you work this out by, let's say, calculator, you will see that this is 1.7022 and so on and so forth. Okay. On the other hand, if you compute the value for the linearization, and that is equal to 2.1 for negative 0.1. And then if you work this out, you will see that this is 1.7. So you can verify that those are pretty close. Okay, so this is the idea of linearization. In a way, this is pretty good because f of xy could be something very complicated, like this example. But by linear approximation, you could approximate some complicated function by a simple function like this. Okay, now, so that's about linear approximation. And then for the rest of the video, I'm going to talk about the concept called differential. Okay, then now, let's go back to our setup. Given z is equal to f of xy and ABC is a given point, and the C is of course ABC. So given point on the surface, so C is equal to f of AB. And then now, by the linear approximation, let's go back to this. Of course, you could just bring this to the other side. And f of xy is z value. So the linear approximation gives you z minus c is approximated by the partial derivative at AB, x minus a, plus partial derivative AB, y minus b. Okay, then now, so then we can view this in the following way. Suppose you are at ABC, where x is a, y is b, and then c is automatically determined. And then if you increase your x value a little bit from a, and if you increase y value a little bit from b, that means this is the increase in x, so it's a delta x, and this is delta y. And then your z value increases a little bit, delta z. That's the increase in the z value. So in a way, linear approximation here tells you how much the z value increases if you increase x value and y value a little bit. So this is written as delta z increase in z is approximated by the partial derivative times the increase in x plus partial derivative and the increase in y. Then now, here's a little trick in calculus. Let's take the limit where the increases in x and y get closer and closer to 0. So delta x goes to 0 and delta y goes to 0. And then in calculus, they often do like this. If you take the limit, delta becomes d. dy. So, therefore, this is written as, of course, the partial derivative. This is a partial derivative. So another notation for the partial derivative is partial f, partial x, dx plus partial f, partial y, dy. Now we get this sort of like a mysterious looking expression. And this is called the differential of z is equal to f of xy, or sometimes people call it total differential. Total differential. Or simply differential of z is equal to f of x, y. Okay. And then, like I said, this expression is a little bit mysterious in a way, but there's an analogous expression in calculus 1 or 2, so in R2, namely calculus 1 or 2, suppose you are given y is equal to f of x. Okay, and then the linear approximation for y is equal to f of x is given this way. And so delta y, so that means the increase in y value is approximated by the derivative. And then if you take the limit, delta x goes to 0, what you get is dy is equal to the derivative d. But then now dx, but let's just say, okay, so what's delta x? Delta x is x minus a, right? So if delta x goes to 0, x goes to a, so a becomes x. You get this expression like this. And then now this is, of course, rewritten as dy over dx if you divide both sides by dx. And then this is just a derivative, the formula for the derivative. And then this is indeed differential of y is equal to f of x. So in a way, the expression here is a generalization of this familiar expression. But strictly speaking, I haven't really given a precise statement about what this means. And indeed, here, the cheat is here. Cheat is here. And then, if we take the limit, delta z, delta x, delta y become dz, dx, dy. Okay. But in calculus, we often use symbol like dx, dy, whatever, without precisely defining what that is, right? So the derivative is defined precisely in terms of limit. And then originally this symbol is introduced as another notation for the derivative. Then how can you actually treat this like a fraction? And how can we write in this way? Well, no one really justifies it in calculus. But as it turns out, if you go to like more advanced level in mathematics, well, actually almost graduate school, if you go to graduate school, there is a precise definition of symbols like dx, dy, dz, and so on. And according to the precise definition, indeed, you do have this expression. But of course, in this course, we are not going to go into the detail. So you may just think of this as just an expression and then interpret this as follows. If you increase x a little bit and y a little bit, and then the increase in z value is given this way. Okay, that's what this formula means, and you may just think of it as it is. Okay, so that's essentially a differential. And then let me just give you one more remark related to this. So given z is equal to f of x. So like I said, increase in z value is approximated by expression like this. But precise increase in the z value is actually written as this: a plus b delta x plus f of y ab delta y plus some error terms. So there are some error terms for each of the variables x and y, which I call epsilon 1 delta x plus epsilon 2 delta y. And so those are, so to speak, error terms. Error terms. And then, strictly speaking, the function z is equal to f of xy is said to be differentiable differentiable. At given point A and B, if those two error terms go to 0 as you take the limit. Remember, for y is equal to f of x, differentiable means the derivative exists, namely the limit for the derivative converges to some point. And that's what the differentiability means. Now, in functions with two variables, what does differentiable mean? Well, differentiable means actually this. It doesn't mean that two of the partial derivatives exist, okay, but it means that the error terms go away in the linear approximation. But in practice, here's a theorem. If both f sub x partial derivatives viewed as a function of x and y, and f sub y xy are continuous, if the two partial derivatives are continuous at this given point AB, then it's differentiable. Differentiable at AB, meaning that those error terms go to 0. And in this course, we are not going to really care much about this level of theoretical issues. But there are some exercise problems in WebAssign, a very small number of exercise problems about this issue. So I just explained this. Anyway, so that's all I have to say about this section.